Space, the final frontier. One day I will remember where that was from, but let's revise space physics. Now, the last unit in our syllabus, and it's not too hard, it's the newest edition, so you will only ever see questions in Unit 6, starting 2023 up until now. Okay? Was it Star Trek? Maybe it was. It's been ages since I've watched anything good. So this unit is actually, at least in my head, split into 3 to 4 different categories. We talk about planet Earth, that's what we'll start with. We'll then talk about the solar system and how solar systems were formed. We'll talk about stars and how stars were formed, like the full life cycle of a star, and distances in space and such. And then finally, we'll talk about the universe and the Big Bang theory, so the concept of the Big Bang. As a friendly reminder again, please remember that these little, checklists over here, like these sentences, are things that you should read. These are directly from the syllabus. Use them as a checklist to make sure that you understand the topic. So, for example, when we're done, you read that, hey, that you know that Earth orbits the sun once in approximately 365 days, and use this to explain the periodic nature of seasons. You at least understand that. If you realize that you don't understand something, revise that again. So let's get started with Earth, the planet that we're on, the third planet from the sun, the one with an atmosphere and the one that we're ruining. So, what about Earth? A few details. First, Earth is a planet. Okay, that was supposed to turn into a joke, but it's already a joke on its own. So, Earth is a planet. And there are 3 things about Earth that I want you to remember. There are 3 rotations, essentially, that I want you to remember. First, the fact that Earth rotates around itself. So the Earth spins around itself once every 24 hours. And that's what we call a day. So the orbital period or the orbital rotation is 24 hours. Now, because of the fact that Earth orbits around itself, this is the reason why you have day and night. Because sunlight comes in from one side of the Earth, lighting up half of the Earth, and the other half is basically dark. And it takes 24 hours to go through. So that's why you see the sun moving in the sky. Then, Earth takes about 365 days to finish one orbit around the sun. So when I say the word orbit, I mean it's rotating with something else being the center. So notice how I didn't say the Earth orbits around itself. No, I just said it rotates about itself. However, Earth orbits the sun, and that takes 365 days. Now I know you know that I know that you know that it takes 365.25 days. So you get a leap year every 4 years, but ignore that. It's just 365. Okay. But one more thing though. When Earth spins around itself, its axis is tilted. So it doesn't spin around itself like this. No, it takes an angle and then it spins. So the countries over here spin this way. That's where the equator is. Now here's the thing though. Because of the tilt of the Earth, it's not a perfect sphere, it's like a tilted sphere and it spins. You end up getting seasons. If we zoom in to this diagram, the reason we have seasons is because when the Earth is tilted this way, like I want you to look at the diagram on the right, and you look at the distance that the sun's rays have to travel in order to get to the northern or the southern hemisphere. I'm going for the extremes though. The northern hemisphere needs a little bit more time than the southern hemisphere. Like it takes more time for the sunlight to reach it, or it travels a longer distance, which means the southern hemisphere is technically closer than the north, so it gets more daylight hours than the north. So the northern hemisphere becomes cold because it gets basically less sunlight, and the southern hemisphere becomes hot, which is what gives us a southern summer and a northern winter. So right now, if it's cold these days, it's winter. That's summer down in South Africa, in South America, in Australia, all of these places. But then, when the Earth orbits the sun and goes to the other side, the tilted axis is the same. Like the axis itself hasn't changed. So over here, here's your axis, which means the northern hemisphere is now technically closer than the south. So it's the northern hemisphere that gets hot. So now we get summer. And the southern hemisphere is what gets cold. It's winter. Obviously, spring and autumn are just like transition seasons. So when the winter turns into a summer, we call that spring. When the summer turns to winter, we call that autumn. But weather-wise, they're both basically the same. Okay, very good. Let's move on. The third rotation I want you to keep in mind, because I said two, third one, isn't the Earth's rotation. It's the moon's orbiting of the Earth. The moon orbits the Earth. It goes around. And the moon takes around 1 month to finish going around the Earth once, which means the Earth is the center of the moon's orbit. Okay. Now, the reason we see the moon is because the moon reflects sunlight, the light from the sun. But depending on where the moon is, you get different phases of the moon. For example, here's the sun. Ta-da! And it's shining light onto the moon and Earth, obviously. But when the moon is here, the moon is here, between you and the sun, you see nothing. Because technically speaking, if this is the moon, the sunlight hits the back of the moon and reflects, but you're on the other side, so you see nothing. It's all dark. Brr. So we call this a new moon. This is the start of what we call a lunar month, right? A new moon. Completely black, dark. But then slowly as the moon starts to move around the earth, the moon starts getting gradually brighter and brighter until you see half of the moon being bright. This takes around 7 days, and this is what we call the first quarter of the month. Now, the reason you only see half of the moon bright is because now you're to the side of the moon, so you get the bright light from the bright half, but you also see the darkness from the other side. Then if you wait for another 7 days and the moon gradually gets brighter and brighter and brighter, at day 14, so another quarter of a month away, you end up seeing what we call the full moon, which is when you are technically here. Because all of the sunlight gets to you. Yay, I see a big round bright circle. I don't see the dark side of the moon. If you wait for another quarter, you end up with what we call the third quarter or the last quarter, which means you end up seeing half of the moon bright again. But because you're now on the other side of the moon, like I'm here, to me, it's now the left side that's bright and not the right, because where I'm standing has technically changed. Sure, it's the moon that's moved around, but me relative to the moon, I'm technically looking at the other side. So you get the last quarter, or what we call the third quarter. It's also called the third quarter. And then it goes back and we start a new moon again. This happens after another 7 days, by the way. So after about 21 days. Good? Yeah. The phases between a new moon and a first quarter or a new moon last quarter is called a crescent. That's when you get like a little banana of light. And then when it starts getting brighter and brighter, between a quarter and a full moon, we call this a gibbous. That's when you get a banana of dark and everything else is bright. But we have two different actions going on. When you're moving from the new moon to the full moon, this entire process is called waxing. Because it's like you're polishing the moon so it's getting brighter. And when you're moving from the full moon to the new moon, we call this process waning because it's getting weaker, right? So wane means getting weaker, not Bruce Wayne as in Batman. Okay. What you need to remember, primarily at least, are the main phases. Like, are these main phases? When does a new moon happen? What's the first quarter? What's the full moon? What's the third quarter? What's the new moon? And so on. Okay. I'll be honest with you guys. Like the whole gibbous, and the crescent and waxing and waning has not shown up in questions yet. So it not might not be important. But we'll talk about them just in case. Finally, Bal. How fast is the moon going around the Earth? We call that the orbital speed. And we calculate the orbital speed using distance over time. But if you look at the formula, it's what? What's that? 2 pi r? What's that? The distance traveled around a circle this way is called the perimeter or the circumference of the circle. And the circumference of a circle is 2 pi r, where r is the radius of that circle. So if I want to calculate the orbital speed, I use 2 pi r, which is the circumference, over the t, which is called the orbital period, the time of one orbit. So far, there are only two periods that you really need to remember, orbital periods, that is. The moon, which is 1 month, it's often approximated to 30 days. And the Earth's orbital period, which is 365 days, which is 1 year. Okay? Very good. Next, let's solve a question or two. First off, the time taken for Mars to orbit the Sun is 690 days. The average orbital radius is 2.28 10 to the power of 8 kilometers. An Earth day is 24 hours. What is the average orbital speed of Mars in kilometers per second? Okay, that's kind of silly, but let's get started. Speed is 2 pi r over t. 2 pi, and what's the r? He said the orbital radius of Mars is 2.28, so 2.28 times 10 to the power of 8. Should I convert the units? No, I don't. Because this is in kilometers, yes, sure. But he also wants the speed in kilometers per second. So I'm keeping it as kilometers. Divided by time, which is 24 hours. This I change. So from 24 hours to minutes is times 60. From minutes to seconds is another times 60. So you end up with 2 pi times 2.28 10 to the power of 8 over 24 times 60 times 60. And this gives me 16,581 or 80.6. I can write this down in standard form, and I'd like to. 1.66 10 to the power of 4. All right? Very good. Is that right, guys? Bravo! You noticed the trick. What's the trick? It's not 24. It's what? 24 is one Earth day. I'm not using Earth days. Sure, the reason why he said Earth days to remind you that a day is 24 hours. Mars takes 690 Earth days. So we multiply this by what? 690. Good job. I love that you guys are focused. Excellent. Which gives me 24. That's a much nicer number, don't you think? Or 24.029, whatever, but 24 kilometers per second. That's pretty fast, actually, if you think about it. Next. Which data is needed to calculate the average orbital speed of a satellite around a planet. Wait, what? Okay. The distance from the satellite to the center of the planet. Yes, I need that, right? The radius of the planet. I don't need that. Why not? Because I already have the distance from the satellite to the center of the planet. The period of the orbit rotation of the planet. Do I care about the time that the planet rotates about itself? The time taken for the satellite to orbit the planet. Absolutely, because I want the time taken for the satellite to go around. I want the planet to go around itself. So which choice gives you the first and the last one? That would be B. Next. Approximately how long does it take the moon to make one complete orbit? We just said it's a month, so B is the answer. Next. State the symbols, state the equation, sorry, that defines the average orbital speed, V of a planet. State the meanings of any symbols you use. So if I write down as this, V equals 2 pi R over T, I then have to give him a key and say that R is the orbital distance, or the distance from the center of the planet, right? And capital T is the orbital period, or the time taken to complete one orbit around the sun, or for the planet to complete one orbit. Okay. Suggest why countries that are a significant distance from the equator experience significant temperature variation throughout the year. This is a really nice question, actually. So let me remind you of something. What's the equator again? Like, to those of you who don't know, what's the equator? This line over here is the equator, right? Now, if you haven't noticed, if no matter whether it's like summer or winter, if you're on the equator or near the equator, so somewhere here, even when the sun comes in from the other side, you're technically, if you think about it, technically you get roughly the same amount of sunlight. Roughly. It's not perfect, but it's almost the same. A little bit more during the summer, just a little bit less during the winter. But look at something that's on or near the pole. Let's grab the South Pole for a second, or like North Pole, because nothing's on the South Pole. So let's say you live here, right? You get lots of daylight, right? Or actually, when you're up here, you don't get a lot of daylight because this is going to be a northern winter, right? Because you're really far away. Most of the time, you're in the dark. But when the sun starts to come in from the other side, now you're facing the sun a lot. You're getting a lot more daylight, a lot less nighttime. Oh, so because you get more daylight, more nighttime, like at the extremes during summer and during winter, you're a lot what? Hotter during the summer because you get more daylight. And you're a lot colder during the winter because you get less daylight in general. Okay? Does everybody understand what I'm talking about? When you're at the poles. That's what he means by a significant difference away from the equator. Okay? So all we'll say is what? The sunlight or the sun rays, that's only one mark. Does what? Strikes those countries for an extremely different number of hours per day throughout the year. A lot more during the summer and a lot less during the winter. So the daylight hours of those countries vary significantly throughout the year, right? Okay, very good. Next. Next up, solar system. Oh, you have a giant list of things to go through, but it's not that big. It's just because you got a lot of things you have to name. Okay. First, our solar system. A solar system in general consists of a bunch of different things floating around. You need to know what those things are. It consists of a star, for example, called the sun. Any solar system starts off with a star, but our solar system is a star. It has 8 planets. So planets are things that orbit the sun. Is there anything else that orbits the sun? Yes. You have minor planets such as Pluto and asteroids, these little rocks in the asteroid belt. All right. You also have moons that orbit the planets. And then you have some random little bodies that move around the solar system, like comets. They also orbit the sun, but they have extremely skewed orbits. We'll talk about them later. And other satellites, moons essentially. Now, if you look at our solar system again, and you look at the planets in order, let's zoom in. So, what is the order of the planets? The sun first, then you have Mercury, Venus, Earth, and Mars. So you have to know them in order. We are here, just so you know. Women come from Venus, men come from Mars, and we had to meet up here somewhere. Like, haha. That's the name of a book, if you don't know. Then you get to the big planets, then, the large gassy giants. The one with an eye like a beholder is called Jupiter. Then when the rings, lots of rings, is called Saturn. Then the butt of all space jokes, Uranus. And then finally, the poor gas giant behind Uranus, Neptune. Okay? You have to memorize them in order. But one more feature though. The planets near the sun are small and rocky, whereas the planets far away from the sun are large and gassy, or gaseous essentially. They're made mostly of gas. Why? This has to do with what do we call the accretion model of the solar system. Basically, the solar system was formed the following way. We start off with what we call a nebula, which is just a cloud of dust and gas floating in outer space. That's the start of any solar system. And then over time, gravity eventually starts forming in the middle of that nebula, right? Which pulls in, honestly, primarily hydrogen gas. So you primarily have hydrogen being pulled in. And then it starts to what? Hydrogen gets fused, and then its temperature increases because it's, colliding with each other. It experiences a lot of pressure, and eventually nuclear fusion starts. That's when that little ball of, hydrogen, which we call a protostar, this is called the nebula. The protostar eventually turns into a nice big stable what? Star. Now, one additional thing. What's inside a stable star is just a bunch of hydrogen and helium. We'll talk about that again. But a stable star is only considered stable, like it's done becoming a star and it's now just like is when two forces inside a star balance out. You've got the force of gravity pulling everything in. So you've got gravity pulling everything in. And then because the star gets really hot from nuclear fusion, you've got a lot of hot air or like hot wind, essentially, the expansion of the heat of the sun from the heat pushing outwards. So you've got the outward force of the heat, so force of heat. A star is stable when these two forces are equal. So gravity is not stronger than the heat, which pulls it in, and the heat's not stronger than gravity, which makes it expand. Okay? So that's when a star becomes stable. That still doesn't explain the rest of the solar system, though. Well, sure. Now, when the star is stable, everything else in the solar system, the rest of this nebula, the rest of the dust and gas, starts spinning around the sun. You have lots and lots of what? Dust and gas spinning around the sun. We call this the accretion disk, right? So they're spinning in a big flat disk. This is because gravity applies a force on them, which causes them to spin, going around in a circle. So circular motion, essentially. Then what? Slowly over time, inside the accretion disk, all of the dust and gas, primarily dust, starts clumping up together. Like, you know, when you've got a bunch of dust and they start to stick together and they start getting bigger and bigger and bigger. That process is called accretion, when you have like an object that is slowly formed by clumping up material on top of each other. These little clumps are called protoplanets because they're still not planets. But when they're done completely sucking up all of the dust around them and you don't have a lot left, they form what we call planets. So when you have a nice stable star that's glowing in outer space, lots of heat and light and other types of waves from it, you end up with these big clumps of matter that orbit the sun. And we call these planets. Okay? Now, so let's go through the steps again. You just need to remember the steps again. Solar system begins as, ball of dust and gas. You don't have to use the word swirling, for example. It's a bit too colorful. Dust and gas called a nebula. Then gravity pulls mass to the center, which forms a protostar. The word proto in space means in the process of becoming. So it's going to become a star. It's still forming into a star. And then it becomes a stable star when the inner force or inward force of gravity is equal to the outward force of the heat. Then any mass that's still left outside the nebula, which is a lot, starts spinning in a disk called an accretion disk. And then gravity starts clumping all of dust and gas to make larger rocks that orbit the sun that are called planets and protoplanets. Now, that doesn't still explain why the four planets close to the sun are small and rocky. Well, when the solar system was being formed, the heat from the sun, which we will call solar winds, pushes the lighter elements. So think hydrogen, helium, oxygen, nitrogen, those kinds of things. They get pushed out towards the outer edge of the solar system. And the heavier elements, so think, iron and, some carbon and everything else, the heavy elements get left close to the sun. So when the planets were forming, the ones close to the sun only had mostly heavy elements to pull from. There's some gas, but mostly heavy elements, so they're small and rocky. Whereas the four planets far away are mostly made of gas because that was all there was. So how do we explain that? We say that the heat from the sun, or what we call solar winds, pushes the lighter elements further away. So the closer planets were made of heavy or rocky elements, far planets were made of gases. Very good. Yeah. You'll notice that we mentioned the word gravity a lot. Gravity is the most important and most fundamental force of nature. And everything that has mass has gravity. But how strong is a planet's or a sun's gravitational field depends on two things. Number one, the mass. So the bigger the mass of the planet or the sun, the stronger the gravitational field. It gets really strong gravity. And the farther away you are, the weaker the gravitational field strength, which again makes sense. Now, this means that the sun has most of the mass of the solar system. How do I know that? Because everything orbits the sun. All the planets, all these big, heavy, chunky planets orbit the sun, which means the sun has the strongest gravitational field of everything in the solar system. So it's keeping everything in orbit around it. It's got the strongest field. Okay? Good. Moving on. Now, remember when I said, comets have this weird orbit to them? Let's talk about orbits. There are two general shapes for an orbit. A circle, which is the orbit of most moons, by the way, and some planets, and elliptical, which is more of an oval kind of shape. And almost all planets have an elliptical orbit, not a circular one. We just assume it's almost circular, by the way. That's why we can use the equation 2 pi r over t, because we assume it's like a circle with a constant radius, and it's fine. But all of the planets, minor planets, comets, they all have what we call elliptical orbits. Okay? That also means that the sun is not perfectly in the center of the orbit, because ellipses don't have a centered center, essentially. They have what we call a skewed or an eccentric center. Okay. So it's not perfectly in the middle either. But the fact that something like a comet is in an elliptical orbit affects two things. The speed, aka the kinetic energy of the comet, and the gravitational potential energy of the comet. When a comet moves further away from the sun, it starts getting faster. The speed increases, the kinetic energy increases, right? No, it decreases. I want you to take the model that we used on Earth and apply it here. When a comet moves away from the sun, or a planet moves away from the sun, it starts moving slower. Why? What type of energy increases as your height essentially increases on Earth? Gravitational. So even things in space have gravitational potential energy compared to what? The sun. Like if we assume sun is their starting base, not the Earth, sun is their start. So as you move farther and farther away from the sun, the distance increases, so the gravitational potential energy increases. This has to come from somewhere. So what happens is your kinetic energy decreases. So as you move further away from the sun, the potential energy increases and the speed decreases. But then as you start shooting slowly towards the sun, you speed up. Again, the force of gravity gets a bit stronger, you start accelerating, and you get really fast when you're close to the sun. The fastest you get is when you're closest to the sun. That's because your kinetic energy increases as your gravitational potential energy decreases. So you move faster over here. Okay? Good. Last thing I want to talk about when it comes to like the solar system itself and the planets and such is analyzing data. What do I mean? There are a few things that you can measure from those different planets. And those pieces of data that you measure tell you different pieces of information about those planets. Some useful, some not so useful. For example, orbital distance, meaning the radius essentially of the orbit around the sun. Obviously, the larger the distance, the weaker the gravitational pull is towards the sun. And not only that, your orbital time also increases. You take more time to orbit the sun, which logically makes sense, right? Like if you're farther away, you have a larger radius in a circle, so you travel a larger distance to finish an orbit, you take more time. Density. What is density? The mass per unit volume. What does that tell us? It tells you the type of material this planet is made of, right? For example, gas giants have a low density. Even though they're big and huge, they have a low density because they're mostly made of what? Gases. Whereas if we get closer to the sun, you have these solid, rocky, smaller planets. They have a much higher density, which means the size of the planet is small and they're heavy at the same time. Let's talk about temperature. You can measure the surface temperature of the sun, by the way. We can measure that. But temperature actually tells us a lot more than what we think. It's not just like, hey, is it hot or cold? It's what is the range of surface temperatures we're talking about? Like, how cold does a planet's surface get? How hot does a planet's surface get? Like, for example, I think the range of temperatures here on Earth is about negative 80 degrees to about 60 degrees Celsius. Like, that's the minimum and maximum that we can get here on Earth. But something like Mars, sorry, not Mars, Mercury, has a temperature range of around negative 180 degrees Celsius to about 260 degrees Celsius, which means planets can be really cold and hot at the same time because the temperature changes from day to night, or be not so cold and not so hot. This is what makes Earth bearable to live on. But what affects temperature? First, how far away the planet is. If you generally see cooler temperatures in general, like on average, the temperatures are just cooler, shift is lower. This means what? It's further away. It doesn't get as hot. Also, the color of the surface can affect temperature. Some planets have bright surfaces. Some planets have very dark surfaces. And the darker the surface, the better an absorber of radiation it is. Okay? And finally, atmosphere. If a planet has atmosphere, like Earth, it has a smaller temperature range. Like it doesn't have a really extremely high and extremely low temperature. Nah. Because an atmosphere stops our planet from getting too hot, like it doesn't absorb too much heat from the sun, but it also stops us from losing heat during the night, or it reduces the heat loss during the night. Atmosphere is very important. Finally, what does the gravitational field strength of the planet tell us? We just mentioned that earlier. Gravitational field strength is affected by mass. So the greater the value of G, the greater the mass of that planet. So the planet is heavier, it has more mass, essentially. And we don't memorize any values of G, except Earth, which is 9.8. And even that's usually given on the front page of an exam. Good. Let's solve a few questions. First one. Pluto is a dwarf planet. Figure 10.1 shows the direction and motion of Pluto as it follows its elliptical orbit around the sun. Oh, yeah, by the way, why is Pluto not considered a planet? This is just trivia. Because it's smaller than the moon. Like, sure, it orbits the sun. It orbits the sun. But the size of Pluto is smaller than our moon. So it's kind of unfair to even call it a planet when it's even not as big as a moon. But it orbits the sun, so we call it a planet. We call it a dwarf planet. Point X is the point in the orbit closest to the sun. So this is the closest, which means it's probably the highest speed. And Y is probably the farthest point away, so it has the lowest speed. The orbital speed of Pluto varies as it orbits the sun. Describe how the speed of Pluto varies as it moves from X to Y and then back to X. Okay, hold on. How does the speed of Pluto vary from X to Y? Oh, it decreases, and then back to X, and then it increases. That's it. So from X to Y, the speed decreases. And then from Y back to X, speed increases. Okay, easy peasy. Now, I haven't explained it yet. Like, you might be, some of you have this tendency of like, hey, I need to write down exactly every piece of information I know for this 1 mark question. You don't need to explain the energies yet. You don't need to explain because when you move further away, the gravitational potential energy increases. We don't do that. Not yet. That's in double I. Explain in terms of energy transfers why Pluto varies this way. The speed of Pluto varies this way. Now I can mention the energy changes, right? Now I can mention the energy changes. So why? Because as Pluto moves further away from the sun, its gravitational potential energy increases and its kinetic energy decreases. But as Pluto moves towards the sun, its GPE turns into kinetic energy. But this font is really huge. I'm gonna make it smaller. Turns into kinetic energy with maximum speed at x and minimum at, or maximum kinetic energy at x and minimum at y. We should edit the properties of this and make this a bit smaller. Okay, this is a lot better. Okay. Nice. Next. The average temperature on the surface of Pluto is 43 Kelvin. Convert this temperature to Celsius. Now we know this. This is more of a thermal physics question, right? So 43 minus 273. To change Kelvin back to Celsius, you subtract 273. That would give us negative 230 degrees Celsius. Okay. Explain the question above. It's exactly what we just said. Didn't we say that as we move closer to the sun, the gravitational potential energy decreases? There's the kinetic. And as you move away from the sun, the gravitational potential energy increases and the kinetic decreases. Right? And where are you the fastest? Here, when you're closest to the sun. Where are you slowest? Here, when you're farthest from the sun. Okay? That's all we're doing. Okay. Next. Pluto has a white surface as shown in figure 10.2. As Pluto rotates, the white surface alternately faces towards and away from the sun. Ooh. Explain how this affects the temperature of Pluto. Now, what do you guys think? White is a what in terms of radiation? White is what? Reflective. It's a good reflector, or it's a poor absorber and emitter of radiation. White is a poor absorber and emitter of radiation. But the black side, the dark side, is going to be what? A good absorber and a good emitter of radiation. So question, don't just say how hot or cold it is. Talk about the maximum and minimums. Let's say, assume for a second, assume that the white surface reaches negative 200 degrees Celsius, or like, that's a bit too much. Let's say negative 100 degrees Celsius up to positive 100 degrees Celsius. Yeah, let's do that. Let's say this is the range of temperatures on the white side. What do you think the range of temperatures on the black side will be? Assume any values. It doesn't matter. I just want to see if you understand the general, gist of things, the sense of things. The black side is a good absorber of heat. So its maximums will be higher. Its maximums will be higher. So plus maybe 200, right? And its minimums will be lower. So maybe at negative 200. Keep in mind, this is what we call a temperature range. The range is bigger. You have lower minimums and higher maximums, both. Okay? Okay. Now, so how does this affect the temperature of Pluto as it rotates on its own axis? How does that affect Pluto as it rotates on its own axis? We'll say the white surface will have what? Mention both the minimums and the maximums. will have lower maximums, temps, and higher minimum temps or temperatures because it is a bad or poor emitter and absorber of radiation. Okay? Does vice versa work? Yes. Like if you decide to talk about the black side instead, that's great. That's great. That's fine. How lower maximum temperatures and it's 400 degrees? What do you mean? I mean, if the white side reaches 100, then the black side is going to reach 200. The maximums will be higher. Because during the day, it doesn't absorb as much heat. And during the night, right, it doesn't emit as much heat. The white side, because it's a bad absorber and a bad emitter. But the black side is a very good absorber, heats up a lot, and it cools down a lot, because it's a good emitter as well. Got it? Got it. Nice. Okay. Very good. Now, let's move on to the next one. Ooh, I remember this. We solved this before, like in class, I think. But this is a really, really, really fun question as far as I'm concerned. Really fun question. It's all about orbits and times and stuff like that. Now, hold on. Yes. Figure 9.1 shows the Sun as the central dot and the planets, Saturn, Jupiter, and Earth, labeled SO, JO, and EO. The planets orbit the Sun anti-clockwise from Earth's orbit, and the planets appear aligned, so they all appear like one behind the other. Assume that Saturn takes 30 years to orbit the Sun, and Jupiter takes 12 years. Oh, I'm going to need these values, so let me highlight. Saturn takes 30 years to orbit, Jupiter takes 12 years to orbit. Yeah, look, it's farther away, it takes more time. On figure 9.1, mark the positions of Saturn and Jupiter 5 years after their original positions. Label these positions S1 and J1 and show your working. Wait, what does he mean? Hmm. Hold on. If it takes, if where will Earth be after 5 years? Let's start there. Let's start where we are. Where is Earth going to be after 5 years? Huh? What do y'all think? Same spot. Bravo. Because it goes around, back, goes around, goes around, goes around 5 times. Cool. In those 5 years, when we finish 5 oscillations, Jupiter's not even going to finish one because it takes 12 years to finish one loop. And Saturn isn't even going to be close. It takes 30 years for Saturn to finish one loop. So the question is, where will they be? One thing to realize is that if something orbits, let's say the sun, how many degrees does it go around as a circle? Like how many angles is in 1 degree? 360 degrees. That's the angle that you cover in one orbit. But if I say that Jupiter, for example, needs 12 years to finish an orbit, but oops, Jupiter only got 5 years. How much of the orbit will it cover in terms of degrees? That's what you need to find out. That's how you get the position. Same thing for Saturn. If I say, oh, Saturn takes 30 years to orbit, but you only give it 5. How far will this rotate? Like, I'm sure it'll rotate a lot less. Like, it'll cover a much smaller angle after the same 5 years. So here's what I do. I'm gonna say Jupiter, or like J1, is going to take 5 years out of the 12 times 360 degrees. So I'm getting the number of degrees it'll travel or pass through in 360. Because if I tell you, for example, that Jupiter takes 6 years, that's half of the orbit. So that's 180 degrees. So 5 out of the 12 times 360 is 150 degrees. Let's do Saturn at the same time so I don't scroll back up and down. Saturn takes 5 years out of 30 years to orbit. So how many degrees will Saturn go through? 60 degrees, which makes sense. Saturn won't go through much. Jupiter will go through a lot more. It's almost half. Now, I would suggest you use a protractor for this. So measure 150 degrees, so roughly around here, and mark where Jupiter is going to be with a J1. And then measure 60 degrees, which is around here, and mark where Saturn is going to be. Actually, it's a little bit more than that. It's here. This is S1. Use a protractor for that. Use a protractor, okay? And go anti-clockwise this way. This is the direction you measure. This is like a 60-degree slice of pizza, and this is like a 150-degree slice of, I don't know if you can call this a slice, but if you're hungry, it's a slice of pizza. Okay. Next. On figure 9.1, the same figure, mark the positions of Saturn and Jupiter 20 years after their original positions. Mark their positions as S2 and J2. Okay, cool. So if I do this, if I say J2, I'll do the same working, is it now goes 20 years out of the... Wait. How do I go more years than my orbital period? This means Jupiter finishes one loop. So it finishes 12 years, it finishes one loop, and then travels a little bit more. So if I were you, I would subtract 12 from that time. Why? Because I know in that 12 it finishes one loop. I don't care about the full loop. I know it goes back where it starts. I want to find out how much is left over. So 20 minus 12 is 8, right? So 8 out of 12, now that's a good number. So you got a little bit left over. Times 360. How many degrees away from the starting point will it be? So 8 over 12 times 360 is 240. Let's do Saturn as well. 20 over 30. We're not even done. Like Saturn still hasn't even finished one loop. Dude's very slow. Like, come on, man. Move faster. Or don't. 240 degrees, 240. They're going to be what? Aligned. They're going to appear aligned again. So if I measure 240 degrees, it should be roughly here. You guys use a protractor though. I would highly recommend a protractor. This is going to be J2 and this is going to be S2. Then state what is observed from the Earth's orbit after 20 years. So what do you see after 20 years? Jupiter and Saturn will be aligned. They will both be just exactly what they were. He mentioned this earlier. From the Earth's orbit, the planets appear aligned. How do you measure 240 degrees with a protractor? Easy. You don't. 240 minus 180 is what? 60. So this is 180 degrees. So you just measure 60 degrees from the bottom. This is 180. All of this is 180. And then this is another 60. That gives you 240. Okay? So put your protractor this way and measure 60 here. There we go. Why do we measure anti-clockwise? Because he said so. See? Dora? Dora the Explorer? What do you see? I see the planets orbiting the sun anti-clockwise. But 10 years after she figures it out. Mashi? Okay? Good. Alhamdulillah. Very nice. Okay, choose two words from the list to describe each planet. Jupiter, large and gaseous, right? This question isn't over yet. Ugh. Large and gaseous. And Earth, small and rocky. Okay. The average density of Jupiter is much less than that of Earth. The gravitational field strength at the surface of Jupiter is greater than the surface of the Earth. Explain how these differences in density and in gravitational field strength are consistent with your answers to CI. So how are these different, or sorry, how do these support, the whole density and gravitational field strength bit? The large and small, the gaseous and rocky. So density gives us what? Gives us the mass per unit volume, but it refers to the nature of the planet. Jupiter is less dense because it's mostly gaseous and it's very large, right? Earth is more dense because it's what? Smaller and therefore rockier. So it's clearly affecting the size. What does gravitational field strength support? The mass, which also is represented by the size. Jupiter has more mass than Earth because it has a stronger gravitational field, and that's why it's larger. Okay? Good. No. We have still like half of this to go. Okay? We still have half of this to go. All right? Good. So let's type in these answers. So how do the differences in density support this? Huh? What does density represent? Or what does density show, essentially? It shows that sorry, I'm finding trouble writing words, saying words now. That Jupiter has a lower density. Why? Because it's mostly gas. Or Earth has a higher density because it's mostly made of rocky substances. What about the gravitational field strength? So Jupiter has a larger gravitational field strength because it has more mass and therefore it's larger. Or Earth has a smaller gravitational field strength because what? It has less mass and it's small. Okay? So I'm just gonna write down a bit of these. So what about density? Jupiter is less dense because it's mostly gas. Let me change the size of the font here. 14 will be good, I think. And then, what about the gravitational field strength? Jupiter has a greater gravitational field strength, which means it has more mass than Jupiter has a greater gravitational field. So it has more mass than Earth. Now, there are three marks though. So clearly we have to say more because gravitational field strength actually requires a little bit more. So sure, has more mass. But keep in mind, Jupiter is less dense, right? But because it's so much larger than Earth, its volume is so much larger than Earth, it still has more A mass. So it has more mass than Earth because its volume is a lot larger than Earth's. So it has more mass. Despite the fact that a Jupiter has less dense. No, density and mass are directly proportional. But density and volume are inversely proportional. So keep that in mind. Density and volume are inversely proportional. So because Jupiter is made mostly of gaseous substances, it has a very large volume. That's why it has a large volume, but I wasn't asked about volume yet. However, gravitational field strength is proportional to mass. So the more mass something has, the more stronger the field strength. Now, the question already mentioned that the field strength of Jupiter is greater than Earth's, which automatically means Jupiter has more mass. How does it have more mass? Because it's so large, it's got more mass inside all of that space, even if it's less dense. Like, by the way, if this is Earth, this is Jupiter. So I think we can fit a lot more gas mass in here than we can like solid mass in here. Okay. The average density of Jupiter is 1,300 kilograms per meter cubed, and the volume is 1.410 to the power 15. Calculate the mass of Jupiter. So this one's easy. Density is mass over volume, so mass is density times volume. The density is 1,300 times the volume, which is 1.410 to the power of 15. Ooh, what do I spy here? Kilometers. He wants it in meters because the density is in meters. So times 1,000 cubed. Because kilo is times 10 to the power of 3 or 1,000, but then it's cubed because even the prefix gets cubed. Keep that in mind. 1,300 times 1.4, 10 to the power of 15, times 1,000 power 3, which is 1.82, 10 to the power of 27 kilograms. Okay. That was a very big chunky question. Like, look at this. This was all one question, by the way. The whole, orbital period and the structure of those planets and what are they made of, and then we used the planetary data to analyze this, and we use density. Now, let's move on and talk about stars. Other stars, not just the sun. Sun is a star, but let's talk about stars in general. What is a star? Star, at least our sun, is a medium-sized star. And what is it made of? Hydrogen and helium. Now, it also emits a lot of energy, and it emits primarily infrared, visible light, and ultraviolet. These are the main things it emits. Now, the sun is full of hydrogen, right? And helium, which means it undergoes nuclear fusion. So the reaction that goes inside is nuclear fusion. Nuclear fusion of hydrogen to helium. We discussed that in nuclear physics. Okay. When is a star stable again? Because it's a very common thing that you'll be asked. When the inward force of gravity equals the outward force of the heat from the fusion reaction. Yeah. This is just one star in our solar system. Now, you have lots of solar systems, and each one of them has a star. And when you have a group of stars, like billions of stars, you have what we call a galaxy. So galaxies are made up of billions of stars. And we, as in us, Earth, our solar system, is in a galaxy called the Milky Way. Like our galaxy is called the Milky Way. So here you have, if this is the universe, here you have a galaxy, here you have a galaxy, here you have a Cadbury, here you have some, bounty, but I prefer the Milky Way here because that's where we're like, ha 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 ha. I'm funny. Sorry. Now, you need to understand something. The size of a galaxy is huge. How huge? The distance or the diameter of at least our galaxy of the Milky Way is 100,000 light years. So what's a light year again? A light year is a distance that we measure in space. It is the distance traveled by light in 1 year, which means if you multiply 3 times 10 to the power of 8 times 365, that's the time of 1 year, times 24 times 60 times 60 to change it to seconds, you end up with 9.5 10 power 15 meters. It's a huge distance. So we don't measure distance in space in meters. We measure distance in space in light years. Okay? So it's 100,000 light years in diameter. Now, let's discuss the life cycle of a star. Like the text is here. I want to focus more on the pictures for now so you understand what's going on. You can go up and read those. Like we earlier said, a solar system starts forming when you have a nebula, and then in the nebula you have a protostar, and then it forms a stable star when the inward force of gravity equals the outward force of the heat from the nuclear fusion reaction. Now, I don't care about the rest of the solar system for now. Ignore it. A star has a very long life, billions of years, but eventually, when the fuel runs out, what fuel? The hydrogen. You keep fusing hydrogen and hydrogen to form helium. Eventually, you run out of these. When you run out of hydrogen to fuel the nuclear fusion reaction, one of two things occurs. If you have a medium-sized star, like the sun, it's a medium-sized star, it expands and becomes what we call a red giant. So it actually, initially, it collapses and then it expands again because it restarts the fusion reaction with heavier elements, and it's called the red giant. When the red giant expands, it actually breaks a few of the planets in the solar system. And when the red giant finally runs out of fuel as well, it leaves behind what we call a white dwarf. This is what the sun used to be. And the planets that were broken up are now called a planetary nebula. Remember, the word nebula just means cloud of dust and gas. Look, so obviously we broke down the planets, so we have tons of dust left behind. But what if it wasn't a medium-sized star? What if it was an extra, extra large star? What we call a massive star. When it collapses and expands again, it doesn't expand into a red giant, it expands into what we call a red supergiant. Say goodbye to the entire solar system. We're all gone. Everything breaks down. But the red supergiant also starts fusing very heavy elements and starts creating things like iron and things like, uranium and things like the elements that are super heavy. But when that reaction runs out, it doesn't just cool down and leave stuff behind. It collapses one more time and explodes into what we call a supernova explosion. This supernova explosion shoots out what we call interstellar nebulas. So stellar or interstellar means it travels throughout the solar systems or into different solar systems or even other galaxies. And when they fly around in other galaxies, they start forming their own, stars and solar systems. So the cycle starts again. But what's left behind in place of the sun, like in place of the star, is either a black hole or a neutron star. And that depends on the mass of that star initially. But we don't get into the mass for now. It's very important that you at least just memorize the sequence, the names of the things in sequence. Okay. Let's solve a few questions about stars. The energy generated in stable stars comes from nuclear reactions. What type of reaction occurs in the sun? Nuclear fusion, right? So hydrogen fuses. So hydrogen nuclei join together to form helium. This is the right one. Then, fill in the gaps in the paragraph about a star. Much more massive than the sun. So big, big, heavy, extra, extra large, star. The stage that follows a stable state in the life cycle is the red supergiant. It then explodes into a supernova to form something. then this leaves behind a something or a something to form an interstellar or a stellar, that's fine, nebula. So it forms a new nebula, a new galaxy, sorry, a new solar system. And this leaves behind either a neutron star or a black hole. Okay. I know some people are often curious about what's a black hole, but today's not the day for that. Finally, which stages in the life cycle of a star are listed in the order that they occur? So we just need to memorize the stages. Interstellar dust cloud, that's good. Stable star, no. These should have been flipped, so no. Protostar to a red giant? No, protostar turns into a stable star, so no. A red giant turns into a white dwarf and then a protostar. What? No. A stable star turns to a red giant, that's correct. And a red giant leaves behind a white dwarf, that's correct. So D. Okay. Next. Complete sentences about the life cycle of a star. Protostars are formed from nebulas. Protostars are formed from nebulas, or you could call them clouds of what? Dust and gas. You can call them clouds of dust and gas. So I'm just going to call them nebula. Then a protostar becomes a stable star when? Oh, that's the common question. Oh, wait. There's something else. Is when something is balanced by something. Oh, so we have to like write them down separately. Is when the inward force of gravity, I don't know why I'm saying that, is balanced by the outward force of the heat from nuclear fusion. Okay? Or due to the high temperature of the star. The initial fuel used to power nuclear reactions in a star is, this one's easy, hydrogen, we just answered that. Stars that are approximately the same size as the sun, okay, so we're talking about the sun now, become red giants, which then form a dash with a white dwarf at the center. We called it a planetary nebula with a white dwarf at the center. You have to use the word planetary, though. You just can't use the word nebula. It has to be planetary because this is dust and gas left behind from the breakage of planets. Okay? Not from the explosion of a supernova. Okay. Last thing. Let's talk about the universe, and specifically the Big Bang Theory. All right? We already mentioned the Milky Way is 100,000 light years in diameter. It's very large. But how do we know that the universe is expanding? Like, that's the whole point of the Big Bang Theory, that the universe is getting bigger. Everything is moving away from each other. There were three, honestly, four, one of them isn't mentioned here, four pieces of evidence that helps us understand the fact that the universe is expanding or supports the concept. The first piece of evidence is that, very distant, very distant stars have their brightness decrease over time. Not a lot, but it does decrease over time. This means that these stars are moving away from us, but stars that are in different galaxies, by the way, not our own. Okay. The second is something called redshift. What is redshift? When we live here on our planet, in our solar system, in our galaxy, and we look at stars within our own galaxy, the wavelength that we get from these stars is the same for the same colors. Red is red, blue is blue, and when we measure the wavelength, they're the same. But when we try to measure the wavelength from different galaxies, like stars from different galaxies, the wavelength of those waves becomes very large, larger than usual. The waves get stretched. So things get a little reddish in color. They get a red tint. They look more red than usual. We call this effect redshift, and it's called the increase in wavelength of any electromagnetic radiation. So you can say of light, but any radiation emitted from receding stars and galaxies. The word receding means galaxies or stars that are moving away from us. And the faster a star is moving away from us, the more that wavelength is shifted. So if I measure two stars far away from us, one of them has a much greater wavelength than the other. Oh, this means it's moving faster. This is moving slower. So that's redshift. Next, what is CMBR, or cosmic microwave background radiation? Right? This is radiation that you can detect anywhere in space, at all points in space. If I throw you out into space next to Mars, next to Mercury, next to Venus, outside of our own solar system, you will always measure some kind of microwave radiation. We call this CMBR. Now, how was it produced? How was it produced? And what does it prove? We say that CMBR, and you can use this abbreviation, by the way, was produced after the universe was formed, like the moment the universe was formed. And it's a lot of energy. It's very high amounts of energy, very high frequency energy. But then as the universe expanded, the radiation also expanded. So remember your spectrum. Gamma rays at the very beginning, and that's the highest frequency, shortest wavelength. But then if you stretch it a bit, it becomes X-rays. Stretch it a bit more, it's now ultraviolet. Stretch it a bit more, it's visible light. Stretch it a bit more, it's infrared. Stretch it a bit more, it's microwaves. And that's what we're saying has happened. The wave produced, or the energy produced from the beginning of the universe, has stretched until now it's in the microwave spectrum. All right. And then finally, the Hubble constant. So what is the Hubble constant? We measured the speed of different galaxies using redshift. We also measured the distance to distant galaxies using the brightness of a star. So we can use brightness to find how far away a star is. And we can use redshift to find how fast the galaxy is. Hubble, who was a scientist, decided to calculate this ratio between how fast the galaxy is and how far away it is, and realized that the ratio is always constant. The ratio of V over D is simply 2.2 times 10 to the power of negative 18 per second. What does that even mean? This actually is the approximate ratio of expansion of the universe. It's how fast the universe is roughly expanding, in a sense, right? But here's the thing, though. The Hubble constant's biggest draw wasn't the fact that it's just a constant of ratio between V and D. Nah, it was something else. Even the most basic of physics students can find out. If you have speed and you have distance, you can get time, right? Because speed is distance over time, which means time is distance over speed. So what do you think will happen if you get the distance divided by the speed of all of these distant galaxies, which gives you the same ratio, by the way? You get the time taken for these galaxies to move far away from us. Assuming we started at the same point, it's how much time it took for it to move away from us, which is what we estimate is the age of the universe. The age of the universe, which is the time taken for things to move away from each other, like from the Big Bang to wherever they are now, is d over v, because time is d over v, which is 1 over h, which is the Hubble constant. And since it's a constant, it's 1 over 2.2 times 10 to the power of negative 18. This gives us how old the universe is, or the age of the universe. Now, you need to memorize this formula, this Hubble constant, and its definition. Now, let's answer the last few sets of questions and finish this off. State the shape of orbits of planets. They're what? Elliptical. I know this was from an earlier section, but still. Then, light from a distant galaxy is redshifted. What does that even mean? Redshift is the increase in wavelength of electromagnetic radiation from receding stars or galaxies. If you forget the term receding, just say from stars or galaxies moving away from us or moving away from Earth. State the quantity that the redshift of a galaxy is used to calculate. So when we do get redshift, what do we get? We get the speed of the receding galaxy. Remember, redshift gives us how fast things are moving away from us. Brightness of a distant supernova or brightness of a distant star gives us the distance away from that supernova. Okay? Yeah. If you gotta go, you gotta go. Bye. Okay. We're gonna keep going. We only have like a page left. Two quantities define the Hubble constant: the speed at which the galaxy is moving away and the distance of the galaxy. What is the relationship between V and D? Ooh, okay. Hold on. H equals V over D. So it's tough to see the relationship when they're on the same side. So let's make V the subject, for example. So V equals H times D, which means V and D are what? Directly proportional. Like I can even plot a graph of D and V and it'll give us a straight line. So they're directly proportional. So it's either A or C. And what's the estimate of it? 2.2 times 10 power negative 18 per second. It's not meters per second. That's the speed of light. It's 2.2, 10 power negative 18 per second. Next. A galaxy is moving away from the Earth with a speed of 33,000 kilometers per second. The value of the Hubble constant is 2.2 times 10 to the power of negative 18 per second. So he's given us the Hubble constant. Maybe I'll use that. Maybe I won't. And he says the galaxy is moving away from us at this speed. What is the distance from the galaxy to the Earth? Give your answer in light years. That's the second trick ever. Anyway, it's not really a trick. It's just, a nuisance. First, we can get the distance. That's H equals V over D, which means D equals V over H. So what's the velocity? 33,000 times 1,000, because that's kilometers, over 2.2 10 to the power of negative 18. Now, I'm going to make sure this is standard form before I start, because clearly the numbers are going to be huge. 33000 times 1,000. I don't know why this is 100. It's supposed to have an extra zero there. Divided by 2.2 10 power negative 18. And we end up with, as expected, a giant value. 1.5 10 to the power of 25. Now, please remember that 1 light year, all right, 1 light year is the distance traveled by light in 1 year. What is the value of a light year? This was earlier on in the stars category. It's 9.5, 10 power 15. Unfortunately, you have to memorize this. You will not find it in the formula sheet. I wish you could. It's not in the list of constants that it's given to you. So 9.5, 10 power 15. So how do I get the number of light years? Well, if you have the total distance and you have the distance of 1 light year, so the number of light years, I'll just call it LYs, is the total distance divided by 1 light year. 1.5, 10 power 25 divided by 9.5, 10 power 15. Why did I change it from kilometers to meters? Because my light year value is in meters. So I can't divide kilometers by meters, right? I can't do that. You end up with 1.58 10 to the power of 9. This is huge. This is huge. I can't even imagine this distance. Okay. Next. Show that 1 light year is 9.5 10 to the power of 15. Oh, this one's nice. How do I show that? distance is equal to speed times time. And then I'll say the speed is 3 times 10 to the power of 8, because that's the speed of light. And the time is 1 year, which is what? 365 days times 24 times 60 times 60. So I can change it to seconds, because this is in meters per second. I want this in seconds. So 3, oh, no, I'm not going to do that. It's just 3 times 10 to the power of 8 times 365 times 24 times 60 times 60. This will give you 9.5 10 to the power of 15. It's actually 9.46, but 9.5 is fine. State one measurement that is taken when determining the speed at which a galaxy is moving away from Earth. Huh. What do I use to find the speed at which a galaxy is moving away from Earth? Huh? What was the quantity again? It was what? The redshift. Remember, it's the redshift that gives us the amount of redshift. It's the redshift that gives us speed. You can say the change in wavelength or the decrease in wavelength. Write down an equation relating V and D. Oh, this one's easy. Huh? H equals HO equals V over D. You can also write it down as V equals HO times D, like rearrange it how you please. And then state how the distance D of a far galaxy can be determined other than by using the equation. So what else do I check to find the distance of a far galaxy? Like I said, we use the brightness, but not the brightness of anything. We always look at the brightest thing ever and see how that changes, right? And the brightest thing ever is the brightness of a supernova. Nothing's brighter than a star exploding and dying, right? Now, next. Last bit. State what is represented in space physics by the symbol HO. Oh, it's called the Hubble constant. It's just that. Write down the equation that defines HO in terms of speed and in terms of the distance. So HO is equal to V over D. The numerical value of HO is 2.2 10 power negative 18. What's the unit? 1 over a second, or per second as power negative 1. Per second. Because it's meters per second, divide by meters, which gives you 1 over a second. Use this value to determine the estimated age of the universe. This is how you should write it down. The age of the universe, which is the time, is equal to d over v, which is equal to 1 over h, which is equal to 1 over 2.2 times 10 to the power of negative 18. And he wants it in seconds, so I'm not changing anything. I remember one time he asked you to change it to years, but this isn't it, so. You end up with 4.55 10 to the power of 17. 4.55 10 to the power of 17 seconds. State when cosmic microwave background radiation was formed and where we detect it coming from. So where was it formed? Where was it formed? It was formed, remember? Go back, go back, go back, go back. This thing, you can memorize this if you want to, was produced or formed shortly after the universe was formed. And where does it come from? Where do we detect it? Everywhere around us. We don't detect it anywhere. We detect it everywhere around us. Okay? Where's the typing thingy? Oh, there it is, the typing thingy. CMBR was formed shortly after the universe started, right? And we detect it coming or we detect it everywhere in space. We detect it where? Everywhere in space. Okay? Excellent. And that, ladies and gentlemen, is space physics. Not too hard, I hope.